Now, let's start our presentation by looking at the evolution from the classical particle system to quantum particle system. Quantum physics is the revolution that overthrew classical physics. Many scientists worked together for 30 years to establish the quantum theory. Max Planck made the initial contribution by proposing that the energies of any harmonic oscillator, such as the atoms in blackbody radiator, in year 1900. E is equal to hv, where h is a constant that is now known as Planck constant, states that the energy E of the fundamental quantum is directly proportional to the frequency V of the oscillator. When explaining the photoelectric phenomena in 1905, Einstein claimed that the radiation itself is likewise quantized using the same formula. Rutherford discovered the nuclear atom in 1911, and Bohr utilized the quantum theory to explain both atomic structure and atomic spectra in 1913. He demonstrated the relationship between the energy levels of the electron and the frequency of light emitted and absorbed. Because classical physics is causal, it is possible to calculate the future by fully understanding the past. Similar to how the perfect future knowledge enables accurate computation of the past. In contrast, quantum physics describes objects as being a unique combination of both particles and waves. We can only predict the future probabilistically given the comprehensive knowledge of the past. Two bombs with identical fuses would strike simultaneously in accordance with classical physics. However, according to quantum physics, two radioactive atoms that are completely similar can and usually do explode at very different times. Even when they are similar, two uranium-238 atoms will typically experience radioactive decay billions of years apart. Physics scientists frequently use a rule to distinguish between classical and quantum physics. It is quantum physics if the Planck constant occurs in the equation. If not, classical physics apply.
Classical particles. Classical particles are distinguishable objects, which means that the individual particles in a system can be tracked. In the other word, the distinguishable classical particles mean that the configuration of particle A in state 1 and particle B in state 2 is different from the case where particle B is in state 1 and particle A is in state 2. Because it is identical but far enough apart to distinguish, so it obeys the Maxwell-Boltzmann statistic. It is also obey Pauli exclusion principle because there is no restriction on filling any numbers of particles in state. This classical statistic is applicable at higher temperature or lower particle density to render quantum effects negligible. As the quantum concentration depends on temperature, high temperatures will put more systems in the classical limit unless they have a very high density. For example, Fermi-Dirac statistic apply to fermions, where the particle obey the Pauli exclusion principle, and Bose-Einstein statistic apply to bosons. So, Bose-Fermi-Dirac and Bose-Einstein become Maxwell-Boltzmann statistic at high temperatures or low concentration. Next, the particles in classical statistics are spinless. Other than that, new microstate is obtained when interchange the particles. Lastly, the size and cell in phase space is orbiting or continuous.
In particle physics, a boson is a type of particle that obeys the rule of Bose-Einstein statistics. These bosons also have a quantum spin which contains an integer value such as 0, 1, -1, -2, 2, and etc. Boson particles does not obey Pauli exclusion principle. Each energy level or states can contain any number of particles, or we can say that there is no restriction on filling any number of particles in the state. This type of particles also have zero or integral spins. Thus, there is no new microstate will arise when interchange the particles. Lastly, at low temperatures, this is exactly what happened at least for non-interacting bosons. The lowest possible quantum states get a big fraction of the particles in it.
Fermion particles. The name fermion was coined by English theoretical physicist Paul Dirac from the surname of Italian physicist Enrico. In particle physics, a fermion is a particle that follows Fermi-Dirac statistic and generally have half-integer spin, which are spin a half, spin 3/2, and etc. Thus, unit for fermion is h bar. Moreover, these particles obey Pauli exclusion principle. Fermions include all quarks and leptons as well as all composite particles made of an odd number of these such as all bands and many atoms and nuclei. Fermion is different from boson, which obey Bose-Einstein statistic. Antisymmetric wave function for a fermionic particle state in an infinite square well potential. Some fermions are elementary particles such as the electron, and some are composite particles such as the protons. According to the spin statistic theorem in relativistic quantum field theory, particles with integer spins are boson, while particles with half-integer spins are known as fermions. In addition to the spin characteristic, fermions have another specific property: they possess conserved baryon or lepton quantum numbers. Therefore, what is usually referred to as the spin statistic relation is in fact a spin statistic quantum number reaction as a consequence of the Pauli exclusion principle. Only one fermion can occupy a particular quantum state at a given time. If multiple fermions have the same special probability distribution, then at least one property of each fermion, such as its spin must be different fermions, are usually associated with matter, whereas bosons are generally carrier particles, although in the current state of particle physics, the distinction between the two concepts is still unclear. Weakly interacting fermions can also display bosonic behavior under extreme conditions. At low temperature, fermions show superfluidity for uncharged particles and superconductivity for charged particles. Composite fermions, such as protons and neutrons, are the key building blocks of everyday matter.
Next, how Maxwell, Boltzmann, Bose, Einstein, and Fermi-Dirac statistics influence the possible states of the system. So these three statistics influence the possible states of the system based on their distinguishability and the restriction on filling particles in state. Let's consider a very simple case in which we have two particles in the box and the box has two single particle states. So how many distinct ways can we put the particle into the two states? Firstly, for Maxwell-Boltzmann statistics, the particles are distinguishable, so we can label them as A and B. In terms of the restriction on filling particles in state, any number of particles can be in any state, which means that there is no restriction. So the states of the system will be AB0, 0AB, AB, and BA. Two of the states have the particles bunched in the same state and another two have them in separate state. Hence, we get a total of 4 states of the system as a whole. For Bose-Einstein statistics, the particles are indistinguishable, so both particles are labeled A. For Bose-Einstein statistics, any number of particles can be in any state, which means that there is no restriction as well. So the states of the system will be AA0, 0AA, and AA. Two of the states have the particles bunched in the same state and another one have them in separate states. Hence, we get a total of 3 states of the system as a whole. And lastly, for Fermi-Dirac statistics, the particles are indistinguishable, so both particles are labeled A. Fermi-Dirac statistics obey Pauli exclusion principle, which stated that not more than one particle can be in any one single particle state. So the state of the system will be AA. none of the states have the particles bunched up as it obeys Pauli exclusion principle. All of the states have the particles in separate states. Hence, we get a total of one state of the system as a whole. So now you know how the type of statistics influence the possible states of the system.